In the discussion of quantum mechanics, today in lecture 10, I shall try to solve the problem particle in one-dimensional box. It will take about 3 lectures to complete these topics, and it is the part 1. I shall elaborately discuss this problem as it plays an important part of this quantum mechanics. So far, the knowledge we have gathered about this quantum mechanical laws, I shall try to apply all these formulations here to solve this problem. It is the system. It is a sketch of this system. It is the one particle of mass m is executing to and fro motions within the box of length L along this x direction. The particle is having this mass m. Whenever no force is acting on this particle except it collides on this wall and rebounds back elastically, means every collision is elastic. The potential energy, this V is also a function of x, so potential energy is equal to 0 within this box, means within this x greater than or equal to 0, less than equal to L, and the potential energy outside of this box equal to infinity. So this is the rough sketch of the system. Since the potential energy changes abruptly, suddenly at these walls, just outside this box, it is better for us to solve this problem in 2 parts separately. First, I shall write the Schrödinger equation outside of this box, and then it is for inside this box. And the Schrödinger equation for this system is d2 psi x dx square plus 2m h cross square e minus vx psi x equals psi is a function of x only. And here the Schrödinger equation for the particle outside of this box, Vx equal to infinity, and so d2 psi x by dx square plus 2m h cross square, h cross is the reduced Planck's constant, e minus infinity into psi x equal to 0. So this one gives this infinity, e minus infinity minus infinity multiplied by some quantity, it is also minus infinity, and psi x equal to 0. So psi x equal to 1 by infinity into d2 psi x by dx square, and 1 by infinity means 0. That means the wave function for this particle outside the box equal to 0. So probability density is also 0, means there is no chance for the particle to be found outside of this box. Now I shall consider the Schrödinger equation for the particle inside the box where Vx equal to 0, potential energy along this x-axis equal to 0. So we may write d2 psi x by dx square plus twice m h cross square into e minus 0 psi x equal to 0. So the next step, this one remains same, 2m e h cross square within bracket psi, and it is psi x equal to 0. So it could be written as this one, d2 psi x by dx square plus k square psi x, k square the term within this bracket, and k square is constant, and constant equal to 2me by h cross square. So general solution of this differential equation is psi x equal to a sin kx plus b cos kx, where a, b are constants. It is a different double quadratic differential equation, so it will give a number of solutions, and say suppose other solutions may also be there, e to the power I kx or e to the power minus I kx, or any linear combinations of these two can also be the solution to this same Schrodinger equation. General solution of the Schrodinger equation within the box of length L is already reduced, and psi x equal to a sin kx plus b cos x. A and b, these two are constants. These constants are to be evaluated to become the appropriate solutions for this system. And putting this boundary, for that purpose, I shall have to insert these boundary conditions, and first boundary condition is that when x equal to 0, this psi x is also 0. Yeah, also psi x equal to 0. So putting this condition 0 equal to a sin x equal to 0, so 0 plus b cos 0 equal to sin 0 equal to 0. So this term is 0, this term is b cos 0 equal to 1 or b equal to 0. So this equation, this general solution now turns into psi x equal to a sin kx. K is the constant. Now we put the second boundary conditions. When x equal to a, psi x equal to a, again psi x equal to 0. Putting this condition 0 equal to a sin k, and instead of x we write a. This wave function now in this case either a will be 0 or sin k equal to 0. But when a equal to 0, this function always is 0 irrespective of this x, means no possibility of finding this particle within this box. It is not possible. Particle is somewhere within this box will remain. So this psi equal to 0, this is not acceptable, this is rejected, and this is the trivial solutions in quantum mechanics. So another possibility, sin kl equal to 0 and equal to sin n pi, where n equal to 0, 1, 2, 3, 4, any positive integer including 0. But n again must not be 0. If n equal to 0, then again this condition should arise, the psi x equal to 0 within this box, and so this 0 is cancelled. 0 value is cancelled, thus n equal to 1, 2, 3, 4, any positive integer. So k square equal to n square pi square divided by l square, but k square we have already taken as 2me by h cross square. So equating this this energy equal to n square into pi square h cross square divided by 2m l square. Better in here write, instead of h cross we write h by 2 pi. Whenever it is written, this pi square will cancel, and then En, it is the energy for this nth state, n square into h square by 8n l square. So En is equal to n square into h square 8n l square. This is the wave function and this is the energy value, and this n defines the state of this system, and minimum value of n equal to 1. Wave function for this system, particularly in 1D box, is psi n x a sin n pi x pi l. For a particular system of definite m and definite l, this psi wave function depends on n and x, and a is normalization constant, and normalization constant will be obtained by putting this normalization condition. The limit 0 to L, this is the length for this particle to be accessible for free movement, and this psi n x square modulus square and dx equal to 1. A square 0 to L sin square n pi x by L dx equal to 0, and by solving this one, as I have already discussed in previous lectures, A equal to root over 2 by L. So the wave function, normalized wave function of this system is this one. Psi n x equal to root over 2 by L sin n pi x by L. Now I like to give some comments on the energy value of this system. The energy En equal to n square into a square divided by 8 n square. And here this energy value is independent of x. It means that the at any position of this particle within this box, energy remains fixed. And this energy equal to px square divided by twice m. Energy remains fixed means px remains fixed and px equal to mvx. So vx also fixed. Means this particle is moving to and fro motion with a constant motion. And second, this energy is also time independent. So at any time, if we calculate this energy, the particle will have the same energy values. So it is called the conservative motion. Conservative motion, as like this conservative family, and the moral values of that family are not changed with the time. Here also the motion will not change with the time. And third one, energy is quantized. If we give a sketch for this energy values, then in terms of this energy levels, then n equal to 1, minimum value of n equal to 1, and E1 equal to a square divided by 8m L square. N equal to 2, E2 equal to 4E1, n equal to 3, E3 equal to 9E1. That means this particle will take this energy in a discrete fashion, not continuously. In between the two energy, the particle cannot accept any energy in between the two or in between the two. Either this particle will take this energy or this energy or this energy. This fourth one, spacing of this energy levels. This is not equispaced, as we have seen. The energy levels are not equispaced. Delta E equal to this minus this. These are the conjugative energy values, and n plus 1 square a square divided by 8m L square minus n square a square divided by 8m L square. So whenever you are solving, twice n plus 1 into it. So this whenever n increases, this delta E also increases. Means the spacing will increase with the value of this quantum number n. And this 0.5 point energy. Putting n equal to 1, we get this 0 point energy. E 0 point energy. 0 point energy equal to then h square divided by 8m L square, and it is not equal to 0. It means 0 means at 0 Kelvin temperature the particle still will execute the motions and will not be at rest, as consider the classical mechanics. Classical mechanics are told that at 0 Kelvin temperature, every particle in every state will cease their motion and remains at rest. Contrary to that concept, quantum mechanics states that even at 0 Kelvin temperature, the particle will continue to move along this axis. Non-zero value of this 0 point energy is also in conformity with this Heisenberg uncertainty principle. That means delta px into delta x almost equal to h approximately. So we can show that if 0 point energy would be 0, it is not 0 actually, but if we think it would be 0, then delta energy px square by 2m equal to 0. In that case, px equal to 0 and delta px again is 0. So delta x are in determining the position of this particle, delta x equal to h by delta px equal to h by 0 equal to infinity. Means this particle, the position of this particle, error determining the positions of this particle within the box is infinity, but it is not possible. This particle must be to be found within this box, so this one is rejected. So 0 point energy will have a certain value and it will not be equal to non-zero. In the uncertainty principle, we can formulate from this 0 point energy. 0 point energy equal to px square by 2m equal to h square divided by 8m L square. So equating this to px equal to plus minus h by 2l. That means px varies from plus h by 2l to minus h by 2l. That means uncertainty in px will be from plus h by 12 to minus h by 12. So delta px, uncertainty in px values, h by 12 minus h by 12 equal to h by l. And this uncertainty in position of this particle is equal to l, as the particle will be somewhere within this box of length l. So delta x equal to l. So putting here delta px into delta x equal to h by l into l equal to h. So this uncertainty principle is derived or formulated from this 0 point energy. Again, this seventh one, free particle, where for the particle there is no restriction to remain inside within this space 0 to L. If the L is large, free to move in any distance, then L is large, and when L is large, so delta E, L is large, L square is more large, then delta E equals to 0. Means energy changes continuously, means energy levels are in contact with each other, no spacing equal to 0. So the energy changes continuously, and for this a free particle. And again, macroscopic bodies, M is large. So when M is large, again delta E, spacing between the energy levels again tends to 0, and so energy changes continuously in this case also. And quantum mechanics need not apply for this macroscopic bodies. It is like that. I can give an example to explain when this energy is changing continuously, or when it is changing discontinuously or a discrete fashion. Suppose this is the first floor. This is the first floor, and this is the second floor, and this one is the height. Here the height, if we keep a slope to ride from first floor to second floor, then here the energy changes. Here the height is changing continuously. That means you can keep your foot anywhere within this slope, and height is changing continuously. If we keep a staircase, these are the steps, and suppose each step is equal to delta h. Each step equal to say 6 inch. 6 inch means say 15 centimeter. So whenever you are making steps to ride from first floor to second floor, means the height is now quantized. You can rest your foot either this point, this place, or this place, or this place. You cannot take this foot in between these two steps. But if this delta h tends to 0, means this difference of the gap of the steps is very low, very small. In that case, it becomes again the slope, and you can keep your foot anywhere within this slope, and height changing continuously. Actually, this system which I am referring here, it is also called potential well. It is also called potential. Say, suppose this is the well, and here is one form of mass L, and this is the wall of this well, and the frog will executing to and fro motion. Is executing to and fro motions along this suppose x directions on this bottom of this well. This the potential energy of this fog is so high. The potential energy is equal to mgh. M the mass of this fog, g the acceleration due to gravity, h is the height of this well. So this fog cannot overcome so much high potential energy barrier. So this fog will remain inside this box. This is some comparison of this particle in 1D box with this fog in a potential well. In comment number 9, it is very important, the spectra of conjugated polyenes. This spectra of conjugated polyenes means double bond, single bond, double bond, single bond. They are present alternatively. And youngest member of this conjugated polyenes is butadiene. And here it contains this 4 pi electrons. And 4 pi electrons are supposed to be mobile, and it can move throughout the whole chain length of this molecule. As a partial theory of partial valency shows this one, pi bonds are moving from this place to this place. It is the free electron molecular orbital model. Free electron molecular orbital model. So in this case, these 4 pi electrons will be arranged in this way. This n equal to 1 pair for n to 2 electrons remaining in there. It is the highest occupied molecular orbital. So whenever this radiation is absorbed by this butadiene, it will transit from this n equal to 2 to n equal to 3. This is this nearest lowest unoccupied molecular orbital. So this electron will move from highest HOMO to LUMO. The delta E, energy difference between these two levels, I can write 3 square A square 8mL square according to this formula, and minus 4A square 8mL square equal to 5A square 8 ml square. This energy is to be supplied by the absorption of the photon. One photon will be absorbed to transit one electron for one molecule, highly selective in nature. So delta E will be equal to h nu, energy of this photon. This energy is to be supplied for this transition, and mu equal to c by lambda. So then hc by lambda equal to 5h square, 8 ml square, 1h will cancel. So lambda equal to 8 ml square c divided by 5h. L here the chain length of this molecule. Here the two double bonds are there, and one carbon single bond, and there requires one end connection. So chain length of this molecule is equal to 2 into 1.34 angstrom. 1.34 angstrom is the bond length of carbon-carbon double bond, and it is 1 into 1.54, it is single bond distance, and this one is the end connection for one single bond. This one equal to 5.76 angstrom, or 5.76 into 10 to the power minus 10 m. If we then mass of this electron m, here the particle is electron, and mass of this electron is 9.1 into 10 to the power minus 31 kg, and this H Planck's constant equal to 6.626 into 10 to the power minus 34 joules second. So whenever we are putting C equal to 3 into 10 to the power 8 meter second inverse. So whenever we are putting all these values, then lambda is found to be calculated 207 into 10 to the power minus 7, and this is equal to 207 nanometer. 10 to the power minus 9 meter. So this is equal to 207 nanometer. The experimental value is found to be 217 nanometer. This, and the frequency or the wavelength of this light to be absorbed by this molecule will be determined by a very important instrument, which is called the spectrophotometer. By means of spectrophotometer, the lambda value could be determined, and there is a nice matching between these two. There is a nice matching equal to of this experimental theoretical value and experimental value. The selection rule for the transition of one particle in 1D box, delta n equal to odd values are allowed. Means delta n equal to 1 to n equal to 3 or n equal to 4 allowed. N equal to 1 to n equal to 3, 4, 5, these are not allowed. Here 2 to 3, this means the difference is odd value, and it is permitted, quantum mechanically allowed.